Did you ever do the nighttime golfing with the glowing balls?
No, it looks like a lot of fun.
Oh, yeah. Yep, let's start with acids and bases. Okay, last semester, did you get to like naming acids? Okay, we're going to review that a little bit. Did you get to, do you know what an oxyacid is? Okay, so we're going to start with some of our most basic definitions because we're going to have to cover all of the spectrum of acids. So you're going to have Arrhenius and Bronsted, and then you will just get the hang of that, and then we'll go to Lewis acids, which is completely different. It's research over the years. There came a group, and they're like, I don't like the way it's been done. I'm going to do it my own way. And so then we got Lewis acids and bases. So, okay. So did you study strong acids, strong bases, weak acids, weak bases? Right. So this, here's a list of strong acids, weak acids. It's not an exhaustive list, but it's a pretty good one. And so, yeah, one of the things to pay attention to, and we can start talking about this now in terms of equilibrium. Your strong acids and strong bases are going to fully dissociate. So you get just the single arrow. Your weak acids and bases are going to partially dissociate. So you end up with an equilibrium. So like, for example, the way a strong acid works is, let's say I have either 2 molar hydrochloric acid, or I'm just going to pull a number out, 4 moles of hydrochloric acid. Like concentration or just moles, doesn't matter. When this dissociates, each one of my ions comes out in the same concentration. They also come out in the exact same number of moles. Does that make sense? This one is a very an acid you see on standardized tests a lot. Come on. Nope. Some of you health people make me sick. You might have ate some today for lunch. Vinegar. All those people exercising and being healthy. Why? You can exercise, you can be healthy all you want, try to stay beautiful, you're all going to end up in a box. That's my job. Part of my job is to make you sad. Okay, so the thing we got to really think about weak acids and bases is you want to start thinking about them in terms of equilibrium. All right. So here are your, here's an idea of some strong bases and some weak bases. Now, the weak bases can be a little tricky. Now, one thing you're going to notice about your strong bases is, first off, predominantly they're going to be what kind of compound? What do you see as common in all of them? Hydroxides, group 1, and then part of group 2 metals. So you see your barium, calcium, strontium, that's group 2. A lot of your strong bases, almost all of them, are going to be hydroxides. I had to put a little box over that thing there because the place where I found this table, that box was all kinds of wrong. But the strong bases dissociate like you would think. The lithium hydroxide separates into the lithium ion, hydroxide ion. Now, you're going to have to start getting your oxidation states. Even if you didn't know hydroxide was a -1, that's a polyatomic ion. You better know lithium's a +1 all the time. Why? It's in column 1. What's one of the common charge ions? Like calcium, why do you think it has two hydroxides on it? +2. So it's in group 2. Now, your weak bases, they can do something different. So take a look here and what happened here. What's different about that? It still put hydroxide in the solution. Right, but it took a proton from water. It didn't, the base itself didn't dissociate, it stole a proton from water. So those can be a little different. Make sure you're paying attention. So like one of your common weak bases is ammonia. It's going to do the same thing. Ammonia is going to take a proton from water. And it's going to become ammonium. Okay, some of our base definitions. We have our acid and base definitions. We have Arrhenius acids and bases. Arrhenius acids increase the concentration of protons in solution. Arrhenius bases increase the concentration of hydroxide in solution. Okay. One thing you're going to need to get used to is we're going to go back and forth between the notation H plus and H3O plus. We use H plus as a shorthand. H3O plus, the hydronium ion, is what actually exists in nature. Why does H plus not exist in nature? Well, it does, but it's not an ion. What is H plus? It's a naked proton. It's particle radiation. It's not an ion. So it's going to find something to annihilate with pretty quick. Okay. Now, very similar, your Bronsted, Lowry acids and bases are very similar. So your Bronsted acids are going to donate protons. Bronsted bases accept protons. And so here you see water mixing with ammonia. In this case, the water is your acid, the ammonia is your base. The ammonia takes a proton, the water donates a proton. Now, you also notice the words on there, conjugate base, conjugate acid. You're going to have to start being able to identify those, because everything's going to come in conjugate pairs. Your acid is going to produce the conjugate base. Your base will produce the conjugate acid. Because like you take your ammonia there, it's your base. It becomes ammonium, which is the conjugate acid. So if you just put that ammonium in solution, it'll donate a proton and form hydroniums. Oh yeah, and there's that acid you were asking about, acetic acid. So here we're looking at our acetic acid dissociation, and we're looking at the conjugate acid-base pairs. So, okay, so which one of these is the acid, which one's the base? Huh? Think of it in terms of Bronsted acid bases. Well, that's one of the conjugates. Bronsted acids do what? Donate a proton. Bronsted bases accept a proton. Which, on the left side, which one donated, which one accepted? Do what? Yeah, so that's your acid. That's your base. So then your base produces the conjugate acid, and your acid produces the conjugate base. And so you have one conjugate pair there, one conjugate pair there. And so the water ammonia reaction here, you see it laid out in terms of its conjugate, its acid base and conjugate pairs. So you're going to want to get used to that idea. Now, we said we're going to start thinking about weak acids and bases in terms of equilibrium. So we want the equilibrium constant expression for this acetic acid dissociation, and it's going to be called your dissociation constant for an acid. You remember we talked about the subscripts? So what you saw Kp, that was for pressure. Your standard K was usually just for concentration. Now, what do you think the subscript for this one's going to be? A. Okay, A is the equilibrium for your acid. And it's going to look like this. Okay. No. Yep, see, it's a liquid. So now instead of just working with gases and solids, we have aqueous and liquid. So this brings in those other phases. And so your liquids and your solids are not going to be a part of your equilibrium constant. Your aqueous and your gases will be. So if you're looking at this and you see anything marked liquid, that stays out of it. So your general expression for your Ka is going to be that. We use this a lot to find the pH of a solution because you notice the concentration of protons there. Because very easily, yeah, we'll start working with that later. The H3O plus, could also just be H plus. That concentration is what we need to figure out pH. You'll see with weak acids and bases, we're going to make ice tables. Yep. All right. So first off, let's write the dissociation equation for HOC6H5. And then part B, for this reaction that's written down here, identify the acid base, the conjugates, and then write the Ka expression for the dissociation. Okay, so part A. This one you might get wrong. It's okay. It's probably the first time you've heard anything like this. Now, if I have, and I'm going to show you another way to write dissociation equations. You've seen it with water in there so far. You can do that. And sometimes you need to for clarity. But if you're just looking for dissociation, we can leave the water out. So we're going to do HOC6H5. And why can I leave the water out? No. Look at the notation. Well, the water is, but look at the notation that I have there. What phase is that in? Aqueous, which means it has to be in water. So if you see aqueous, the water is kind of understood. Now, on the other side, you're going to get your protons. What negative ion will you have? Where did the proton come from? This has to do with acidity. Oh no, we're not on that equation yet. We're worried about this molecule right here. Nope. This compound here is going to lose one of its protons. Yeah, so you get O, C6H5, and the negative. Remember, I have to put the negative on there because if you lose a hydrogen, you become more negative by 1. Every hydrogen you lose, you become more negative by 1. Now, why did I lose the hydrogen there instead of on the other side? Well, yeah, but why there? Why not one of the hydrogens on the C6H5 side? It's easier to lose. Why? Nope, it has to do with the oxygen. So the oxygen is a lot more electronegative. The oxygen pulls electrons towards itself. It's, you know, you already have a much more, you have a polar bond there where your CH bond is not even polar. They share electrons pretty evenly. You're going to find out that CH bonds are very, very strong. So in a case like this, your acidic proton is going to come off the oxygen. That's going to make more sense when we look at, say, for example, carboxylic acids. It's why, I mean, if you have too much salt in your body and you put a bunch of sugar in, that sugar can become acidic. Because in your in the salts, you have these, let's say you have like chloride ions in your body. Chloride is very electronegative. It can bond into that sugar. And with that electronegativity, it starts pulling all the electrons towards itself. And now hydrogens that are a part of that sugar that were never acidic before are now popping off left and right. So, and they'll be attached to oxygens. Okay, so this is this is another way to write dissociation equations. Okay, now we're going to go with this expression right here for part B. Okay, so we need the acid, the base, the conjugate acid, and the conjugate base. What do we think? Acid donates, base accepts. Conjugate base comes from the acid, conjugate acid comes from the base. No, because look here, we have HO, NH3. Yeah, so this would be our acid. That's our base. And so if this is our acid, it's our conjugate base, that makes this our conjugate acid. Those are our conjugate pairs. Now this one looks a little different. It didn't give us up its proton from the oxygen. Why? The first one we did was a neutral compound, gave up its proton from the oxygen. Why did this one do something different? Because nitrogen's still pretty electronegative. Nitrogen-hydrogen bonds are polar, not nearly as polar as oxygen-hydrogen. It's a little more equal there. What do we have on that amine group? Which one's the amine group? The NH3. What's on that amine group that destabilizes it that's going to cause it to lose a proton much easier? It's a positive. That positive charge is destabilizing it, so it's going to lose a proton from there. That positive charge says, I'm very, very proton rich. I want to get rid of one of these. Okay, so now the Ka expression. Well, and there we go. Okay, the strength of acids. So we talked a little bit about strong and weak acids, okay? Some little lists here, like strong acids fully dissociate, but here's something you can start looking for, Ka values. So we talked about equilibrium, and a large Ka value lies really far to the right. A small K value lies very far to the left. That's going to help you decide strong versus weak. So look at some of the Ka values in that list there. Only one of those is a strong acid. And that's only an approximate Ka. It's such a strong acid, it's really almost impossible to measure. Look how much bigger that is than those others. So you're going to see these very large Ka values for your strong acids. If you looked up sulfuric acid, like if you tried to Google the Ka of sulfuric acid, a lot of times you just get K equals large. It's you just know that that first proton is going to fully dissociate. So then you start seeing your weaker acids, and you see how much smaller their Ka values are, how much less likely those are to give off a proton. So take your carbonic acid there, 4.4 times 10 to the negative 7th. If I put that in solution with water, I'm still going to have most of my neutral molecule left. It'll dissociate a very, very little bit. So you can start telling acid strength and base strength by Ka, well, Ka for acid. Just a question when we get there. What will the K value for a base be? What will its subscript be? B. So our bases will be Kb. That one you kind of want to know for when you use the approximation we talked about. And it's again that 10 to the negative third, 10 to the negative, well, okay. 10 to the negative third is still a weak acid. The approximation happens at that 10 to the negative third, 10 to the negative fourth region. Honestly, once you cross the line into like, let's say you cross the line to like a Ka of 1, 5, 10, beyond, stuff like that. It's like 10 to the first, 10 to the second, 10 to the third. Those are going to be your strong acids. I would say crossing that 10 to the 0 line. It's a decent enough approximation. Yeah, pretty much. It's a good rule to follow for now until you get individual cases in more advanced courses and you're learning why that's the case. Okay, so acids can take multiple forms. We have acids called polyprotic acids. So why is sulfuric acid polyprotic? Multiple protons. In this case, we could make it more specific, not just polyprotic. What would we say about it? What's the prefix on protic? Diprotic. 2 protons. And so you see that for these reactions, you start to actually get multiple dissociations. So it's like we're not just going to write H2SO4 plus H2O gives SO4 gives sulfate in 2 hydroniums. We're not just going to write that. We could figure out how much hydronium we have because look at the first equation. That's going to fully dissociate. So however much sulfuric acid I have, that's how much hydronium I'm going to get out of the first equation. The second equation, I have to do an equilibrium calculation. Because that dissociation, your hydrogen sulfate, what was that? That was like somewhere on like the order of 10 to the negative second, something like that. So it's a much weaker acid. So like down here, if you look at your sulfuric acid, that first dissociation, all of it becomes its constituent ions. Notice that the hydrogen sulfate ion is the conjugate base of equation 1 and the acid of equation 2. That makes it a certain kind of compound. We have things called oxyacids. Gave you a structure here of H3PO4, phosphoric acid. All of the acidic protons are bound to what? Bound to oxygens. That is a signature of oxyacids. Your acidic protons are bound to oxygens. Now, as far as naming acids goes, also your oxyacids come from oxyanion families. You see the families here, your sulfate, sulfide, nitrate, nitrite, perchlorate, hypochlorite. These are all parts of the same family. And notice how the only thing that changes is the number of oxygens. I want you to pay attention to the naming scheme. You notice how any ion that has an ATE as its ending changes to IC for its acid name. Any ion that has an ITE for its ending changes to OUS for its acid ending. So if you had phosphate, that becomes phosphoric acid. Phosphite becomes phosphorus acid. So let's see here. Also, if you have the ions that have the prefixes on it, like the per and the hypo, those become parts of the acid name. The ATE, ITE ending rules still apply. Organic acids. We're not going to do a ton with these because you are going to get inundated with these over the next few years. Okay. The first one there is just your simple acetic acid. That's your vinegar molecule. A lot of your organic acids are going to be designated by the carboxyl group. So acetic acid is a carboxylic acid. Your D-glucuronic acid is a carboxylic acid. Your benzoic acid is a carboxylic acid. Look at the structures of those. And also in organic structures, anywhere you see a vertice, that's a carbon. Okay, you'll have to take into account how many hydrogens it might have. If you're asking yourself how many hydrogens might be there, if you see 4 bonds on the carbon, there's no hydrogen. Carbon will want its 4 bonds. So you see there are 2 bonds to the oxygen, to one of the oxygens, 1 to the other oxygen, and 1 to that carbon right there. So that's 4 bonds. So what parts of these are the carboxyl group? It's one of the reasons we write the formula for acetic acid the way we do. COOH. So it's that group right there. That's your carboxyl group. That's why we write acetic acid like that. So a lot of the times these formulas that look kind of random to you, they're written in a way that hint at their structure. So this one's telling you acetic acid is a methyl group bound to a carboxyl group. Why do we call this one benzoic acid? Yeah, it has the benzene ring. And in particular, it comes from, so is it benzoic acid? What would its negative ion be? Benzoic. Benzoic. Mm-hmm. The ATE IC endings go together. You also see again, you could very easily pick out what the acidic protons are going to be there. Now the D-glucuronic acids are like a little more difficult. Sometimes those hydroxyls can let hydrogens off. Most of the time, your acidic proton is going to come off the carboxyl group. That's why we call those functional heads. So if you say, oh, this lipid has been functionalized, a lot of times you got one of those. Now, we talked about something being an acid and then being a base. Water can also be an acid and a base. And that, let's see, did I put the word down? Where did I put the word? Yes, I should highlight it. That means it's amphoteric. Any compound that could be both an acid and a base is called amphoteric. What you see here is a unique reaction called the autoionization of water. What do you think autoionization means? Yeah, ionizes itself. So since it ionizes itself, we have an equation here that's represented as an equilibrium. It goes back and forth, which means that water ionization, autoionization has its own equilibrium constant. What do you think we're going to call that? Kw. So if you look here, you have liquid, liquid, aqueous, aqueous. Can write it that way. You can. Doesn't matter. The other way you can write this, and it's equivalent, is that. Same thing. Now, experiment has shown at 20, we have to figure out what Kw is. It's a constant you can use for a lot of stuff. Experiment shows that at equilibrium, no, well, kind of, but you remember when I told you there's only one situation where you could write water aqueous and I would accept it? This is the time. Because if I took out the second H2O, yes, I could just write water aqueous, means it's a water molecule. It's going to be interacting with other water molecules, and then you get this. But yeah, it's just both of those expressions are equivalent. So a lot of experimentation was done, and this was found at equilibrium, which means that the Kw that's your constant, 1.0 times 10 to the negative 14th. Also keep in mind, your Kw, a lot of your Ks are temperature dependent. So if you get an exam question that says, which one of these will change the value of K? The temperature will. That changes concentrations. Higher temperature, expanded volume, moles over volume, different K. Okay. Let's calculate the concentration of protons given hydroxide. The hydroxides in solution are 7.3 times 10 to the negative 4th molar at 25 Celsius. Identify if the solution is neutral, acidic, or basic. Okay, well, the way we're going to do that is through the fact that we know what Kw is. So we're going to solve this like that. So what, this is going to be 1.0 times 10 to the negative 14th divided by 7.3 times 10 to the negative 4th. So our concentration of protons is going to be 1.4 times 10 to the negative 11th molar. Now, is this acidic, basic, or neutral? Well, there's something real simple we could do. And we'll talk, well, I'm going to go ahead, like we're going to do it now and then we'll talk about it. How do I find pH? Negative log what? Anytime you see this one of your p-values, it's going to be the negative log of something. And it's the negative log of the thing that you see next to it. This is the negative log of your value for your h's. And that's going to be negative log. On your calculator, it's just the button that says log. This is log base 10. Those of you who are in Tim Keith's class should do this without a calculator. The pH is 10.9. So what is it? Basic. Yes. So that's something to keep in mind. So let's talk about that. The pH scale. Your equation for pH is negative log of the concentration of your protons. You could also just rewrite that as negative log of concentration of H3O plus. Same thing. So your pH scale, small pHs is going to be acidic, 7 is neutral. Large pHs up to 14 is going to be basic. Remember, basic also has the term alkaline. pH changes by 1 for every power of 10. That power of 10 change in your concentration of protons. So your pH of 3 has 10 times the concentration of protons as pH 4. pH of 3 has 100 times the concentration of protons as pH of 5. The analog for pH for basic solutions is POH, and that's the negative log of your hydroxide concentration. And to continue with expressions involving the P expression, we could also do it with equilibrium constants. So anytime you see a pK, that's the negative log of your K value. You could have pKa, pKb, all of these, pKw. So let's use this expression to find some more, let's use the logarithm on Kw to find some useful expressions. So remember our Kw is this. Now, what I'm going to do negative log of Kw is negative log of protons times hydroxides. How can I expand this? So log of protons multiplied by hydroxides. How do I expand that? Right. So when I have log of x plus y, that becomes log of x plus log of y. That's how it expands. So I have the negative. And that's going to equal so now you notice negative log of Kw becomes what? What do we call it now? Well, what do we put on the front of it when we take the negative log? pKw. pKw, negative log of protons is what? pH plus the negative log of hydroxides is what? The OH. Now, we can figure out what pKw is. Negative log, and Kw is 1.0 times 10 to the negative 14th. That's going to make this 14.0. This is a very useful expression that we can use in solving problems. Your pH plus your pOH equals 14. Now, what if we need to find concentrations of protons and concentrations of hydroxides from pH or pOH? Well, so if pH equals negative log H plus, how do we reverse a log base 10? What is the anti-log? So the first thing we do, we're going to do log move the negative over there. So remember, your log is technically log base 10. Okay. So if I have log base 10 of x, if I raise my logarithm, exponentiate it with whatever its base is, I reverse the log. Okay. That's why you can use the e to get rid of natural log, because your natural log is log base e. So that means if I do 10 the log of x, I get x. So now that means that my protons are going to have to be 10 to the negative pH. And similarly, so these are just these are expressions you can just plug numbers into. Okay, let's see if we can get through this. So here, antacid purchased at a local drugstore has a pOH of 2.3. Okay, so if a low pH is acidic, what is a low pOH? Basic. So you're using pOH, it's like the reverse. So the low number is now basic. So calculate the pH, the concentration of protons, and the concentration of hydroxides for this solution. Is the antacid acidic or basic? Okay, well, calculate the pH. Well, pH plus pOH equals 14. My pH will equal 14 minus pOH, 14 minus 2.3. The pH is 11.7. Well, you can already answer the last part. This is basic. Now, my protons. Ten to the negative 11.7. My concentration of protons is going to be 2.0 times 10 to the negative 12 molar. Now you could figure out hydroxides two ways. Yeah. So your hydroxides, you can use Kw over H plus, or I use the second one. The pOH is negative 2, so 2.3. You get a pOH of 5.0 times 10 to the negative third molar. So again, you have options on how you solve how you solve these things. Okay, so Let's see here. So one thing to keep in mind is I kind of just made this decision yesterday because of all the stuff I have to do. And I would rather have another day of class to get through material. So we're going to just take exam 3 off the schedule. And so the next exam you have will be the final. So we're just not going to do exam 3. I'd rather have another day of class to get through material.